focus for circles is actually doing some measurements now with the arcs and angles, both central angles and how they relate to their arcs and measure, how inscribed angles relate to arcs and their measure, and how we can find arc measure and arc length. Okay, we've done some of these vocabulary already with our discovery activity within the book, our research, but we will officially define them again. First off is a central angle. And a central angle is an angle with its vertex at the center of a circle. So an angle with its vertex at the center of the circle. So a diagram of a central angle, if this is the center of the circle, would be any angle with that vertex at the center. And we actually, now that we're going into circles, we'll learn that we actually go past 180 degrees now. We could go to 360, a full circle. And in trig, you'll actually go further. There's actually, you learn that there's an infinite amount of angles. 120, 1200, 1400, 15,000. But we're going to concentrate from 0 to 360 degrees. The sum of central angles in a circle always add up to 360 degrees total. It's kind of like two linear pairs, 180 and 180, or a half a circle and a half a circle makes 360 degrees total. Okay, an arc is just a fraction of a circle, or a portion of a circle. For example, if I draw a circle, it's the actual portion or fraction of the outside of the circle. Maybe it's just that. And I actually label it, if it's point A and point B, arc AB. It's just a fraction or a portion of a circle. Moving on, a minor arc. A minor arc is actually what I drew above. But a minor arc, we'll start with a picture again, is an arc with a measure less than 180 degrees. We always use two letters for a minor arc. So this would be minor arc AB, from A to B, a minor arc. Okay. The description would be, basically it's less than a half circle. And the measure, we use a little m for symbol for measure. The measure of arc AB is always less than 180 degrees. So from 0 to 179.99999 would be a minor arc. A major arc would then be the opposite of that. A major arc would be an arc that's greater than 180, but less than 360. So if I draw a circle, and we have now A, B, and C. Now let's say I want to do major arc from A to B to C, that part of the circle. You'd actually label that arc A, B, C. We need three letters, like we learned in class, for a major arc. And that is more than a half circle. And the measure then would be, the measure of arc ABC would be greater than 180 degrees. The only thing left is a semicircle. And a semicircle, we also use three letters. If C is the center, and let's say this is TQR, that means that TR, segment TR, is a diameter, which means that arc TQR is exactly a half a circle. Major arc semicircle TQR. So this is exactly a half a circle. A semicircle. The measure of a semicircle, so the measure of arc TQR is going to be 180 degrees. Exactly. We also defined adjacent arcs in class. And adjacent arcs are arcs that are next to each other. they share an endpoint. So for example, if I had arc AB and I had arc BCD, those would be adjacent because they share the endpoint B. And you don't even need a picture to show that. The arc addition postulate, if you read that, it says the measure of an arc formed by two adjacent arcs is the sum of those arcs. So basically, that it is if Q is a point on arc PR, then the measure of PQ plus the measure of QR equals the measure of arc PQR. Okay. An example of how arcs and central angles are related, we'll learn that if you know a central angle, let's say this angle is 40 degrees, its arc, corresponding arc, so arc, we'll say arc AB, would also be 40 degrees. Central angles and their arcs are the same. Now we have a linear pair here, so we can actually figure out the other central angle, which would be 140 degrees, supplementary to 40, adding to 180. So this arc would also be 140 degrees, equal to its corresponding angle. Okay, the next part of this is let's actually figure some examples out, some arcs. So all I'm giving you is the central angle DAC is 130. Can we find angle EAC? Sure, that's a linear pair, so that's 50 degrees. Can we find the measure of arc BC? Make sure you put your arc symbols here, they don't copy over. The measure of arc BC actually, I think that's supposed to be EC. There is no point B up there. So the measure of arc EC is equal to its corresponding central angle, which is also 50 degrees. Make sure you use degree measures here, symbols, because arc length and measure are different. We're always in degrees. Arc CD is equal to its central angle, 130 degrees. How about major arc ECD? That would be the sum of arc EC and CD. So 50 and 130 actually gives me a semicircle, 180 degrees. Measure of arc CDE. CDE, well, that is from here to D to E. Now, since there's 360 degrees total in a circle, arc CDE is going to be the difference of 360 take away 50. This is the 50. If I take the green arc plus the red arc, or if I take 50 degrees plus my major arc, I should get 360 degrees total. So that gives me a measure of 310 degrees. Here's another one. Pause the video, actually, and see if you can figure this out on your own. Pause the video. Okay, we know that in circle P, PR is 5, which means PQ is 5, because that's also a radius. And the measure of angle QPR is 90. It's a right angle. It's a fourth of a circle, 360 degrees. Find the length of this. Yeah, I don't want the measure. I don't want 90 degrees. That's arc measure. I want the length of a QR. How long is that? So if the radius, let's say, is 5 centimeters, how long is our QR? See if you can figure that out. Now, a hint is going to be to use the circumference formula. So pause the video and see if you can figure it out. Round to the nearest hundredth for this. Okay, so since the circumference or the distance around a circle is pi times diameter, or you can use 2 pi r, in this case, since the radius is 5, our diameter is 10 centimeters. So an exact value, pi times 10, would be 10 pi centimeters for our distance around the entire circle. Now, because 90 degrees is the measure of our arc QR, not the length, it's 1/4 of a circle. We're actually going to take the total circumference and let's divide it by 4 equals. So 10 pi over 4, an exact answer would be 5 pi over 2. Reduce your 10/4 to 5 halves, which is approximately 7.85 centimeters long, which makes sense in this case. So really, we need you don't really need a formula for arc length, but here's the idea. Arc length is the corresponding arc measure, or that arc's measure, so in degrees over 360, that's where we got the 90, or the 1/4, or dividing by 4, because 90 out of 360 is a fourth, times pi times diameter, which is the circumference. So really it's arc measure over 360 times the circumference of the circle. Make sure you know the difference between the measure of an arc and the length of an arc, because I'll ask for both. And if I ask for the measure of the arc and you put 7.85 centimeters, that's not right. Or if I ask for the length of the arc and you tell me 90 degrees, that's not right. Okay, so the measure of an arc is always between 0 and 360. Very important. Arc measure is related to the central angle of the arc. Central angle equals the measure of the arc. Arc length is measured in inches, centimeters, feet, miles, etc. It's the actual length, the distance. It's a portion of the circumference of the circle. Okay, it's a couple of terms that we defined in class. Concentric circles are circles with the same center. Kind of like the ripple effect. So you have a bunch of circles centered at the same point, maybe like a bullseye. Congruent circles are circles with the same size radius. Okay. And congruent arcs now, this is new. Arcs with the same measure in congruent circles are also congruent. Arcs with the same measure, so degree measure, in congruent circles, two circles are congruent, and their measures are congruent, the arcs, then their arcs are congruent. Okay, draw two circles that are similar. Write a conjecture about them. Well, basically, we talked about this already. All circles, you don't need to draw this, all circles are similar because they're one-dimensional. There'll always be a scale factor. Okay, the next page, another type of angle is called an inscribed angle. An inscribed angle has a vertex on the circle. Has vertex on the circle. So maybe something like this, where point A is on the circle. It's the vertex of angle ABC. So angle, or BAC, angle BAC is an inscribed angle. Its vertex is now on the circle, not the center. An intercepted arc, that is the arc formed by the interior of the angle. So we'll talk a lot about angle and its intercepted arc. In my diagram above, the intercepted arc for angle BAC would be arc VC, because that is the inside of that angle on the circle. Okay. First theorem, if an angle is inscribed on a circle, then the measure of that angle equals half. It's not equal now, so if the vertex is on the circle, the intercepted arc and the angle have a 2-to-1 ratio. It's actually half of its intercepted arc. So going back to my diagram, if I know that arc BC has a measure of 80 degrees, then its intercepted inscribed angle, BAC, is actually half of that, 40 degrees. And you can tell it's smaller. It's not equal like a central angle. So central angle is equal to its arc. Inscribed angle is half of its arc. If two inscribed angles of a circle or congruent circles intercept a congruent arcs, then the angles are congruent. This comes in useful maybe when you have something like this. You have a circle, you have one inscribed angle intercepting arc AB, and then you have another inscribed angle, maybe like here, like that. Okay, so I'm going to mark the two angles. This angle would be equal to that angle because they intercept the same arc, AB. Okay, if an inscribed angle of a circle intercepts a semicircle, well, half of a semicircle would be 90 degrees. So then it is a right angle, picture of this would be something like this. If you know that you have a diameter going through the middle, and let's say you have an angle, an inscribed angle, that intercepts the endpoints of a diameter, which means it's a semicircle. Its intercepted arc is a semicircle. This would be half of 180 or 90. If a quadrilateral, the next one is if a four-sided figure, quadrilateral is inscribed in a circle, then opposite angles are supplementary. This is an important one. Opposite angles are supplementary, meaning they add to make 180. So this diagram might be something like this. I get a four-sided shape. Any four-sided shape that's inscribed, so every vertex is on the circle for this quadrilateral. Opposite angles are supplementary. So if this is 80 degrees, this would be 100. Okay? Opposite angles would be supplementary. Here's an example. In a circle Q, AC is a diameter, that's important, so semicircle. Measure of arc CD is 68, so that's right here. Make sure you label. Measure of arc BE, so from here to here is 96 degrees. Find the measure of angle ABC, BDE, CED, and AED. Measure of arc 80. So let's start with angle ABC. Okay, angle ABC is inscribed in a semicircle. AC is a diameter, so ABC would be half of 180, half of its intercepted arc. This would be 90 degrees. Measure of BDE. So BDE is this one. Okay. We know arc BE is 96. Angle BDE is an inscribed angle with an intercepted arc of 96 degrees, which means that the angle BDE is half of its intercepted arc. Half of 96 is 48 degrees. Angle CED. Angle CED is right there. Its intercepted arc is 68. CED, angle CED, is also inscribed, which means it is half of its intercepted arc. Half of 68 is 34 degrees. Arc AD is the last one. Arc A to D. A to D. Okay. Well, we know that arc CD is 68, and we know also that segment AC is a diameter. So arc AEC or arc EDC, this entire arc from here all the way around to here is going to be 180 degrees. It's a semicircle, which means arc AD is supplementary to the 68, because arc AD and arc DC make a semicircle, 180 degrees. So we take 180 minus 68, and we should get 112 degrees. Okay. Next example. In circle X, angle 4 is 7x plus 3, angle 5 is 7x plus 3, angle 1 is 5x. Find angle 1, 2, 4, and 5. 1, 2, 4, and 5. Okay, well, remember that opposite angles in an inscribed quadrilateral are supplementary. Okay, so let's see, we got angle 4 is 7x plus 3, angle 5, angle 5 is 7x plus 3, and angle 1 is 5x. Okay, find angle 1, 2, 4, and 5. So how do we do this? Well, we'd start with, first of all, if you look at angle 6 has to be 90 degrees because it's inscribed in a semicircle. Half of 180 is 90, which means angle 4 and angle 5 have to be also 90 degrees together, or 90. Angle 6, 4, and 5. 4, 5, and 6 make a triangle. So we would add all three up to make 180. So 7x plus 3 plus 7x plus 3 plus 90 for that triangle is 180. Combine your like terms. You got 14x's, 3, 3, and 90 makes 96. Solve that equation. You're going to get a value for x. Okay? So you're going to take 180 minus 96, which is 84, divided by 4. You should get x is 6. Now that's not the answer. They want us to find the measures of 1, 2, 4, and 5. So I'm going to plug x in, or plug 6 in for all these x's. So let's start with angle 1. Angle 1 is 5x. So 5 times 6 gives me 30 degrees. Angle 2. Okay, we don't know angle 2 yet, so we'll skip that. Okay, angle 4. Angle 4 is 7x plus 3. So 7 times 6 plus 3. That's going to be 45 degrees. So the same with 5, because 5 was the exact same. You're going to get 45 degrees for that one. Okay, so we got 45, 45, 90. We got 30 for angle 1. We know that angle 3 is a right angle for the same reason 6 is. So what type of right triangle is on the bottom? We got 30, which means angle 2 has to be 60 degrees to make that a triangle through 1, 2, and 3. Okay, last example in this part. Quadrilateral QRST is inscribed in circle C. This one actually goes a little faster. Angle T is 95, labeled already. Angle S is 100, labeled already. Find Q and R. Remember, opposite angles are supplementary. So these two are supplementary. So the measure of angle Q will be the supplement of 100, which is 80 degrees. 180 minus 100. Angle R is supplementary to angle 95, the 95 degree angle. So the measure of angle R will be the supplement of 95, which is 85 degrees. All right, last page. Arcs and chords. So we got different types of chord. A chord, remember, is a segment with endpoints on the circle. When a minor arc and a chord share the same endpoints, we call the arc of the chord. So arc BC is the arc of segment BC, which again, now this is why notation is important. Arc BC versus segment BC is written different, and BC is a chord. So we'll chord BC. Okay? An inscribed polygon, we kind of define that. That's a polygon with all vertices of that polygon on the circle. So if it's a pentagon with 5 sides, all 5 vertices are on the circle. Okay? We talked about this already last. In circular or incongruent circles, 2 minor arcs are congruent if and only if, and actually this is new, sorry, their corresponding chords are congruent. So, for example, if I had 2 circles like this, and we knew the circles were the same, and I had the same size chord in 2 different circles, we would know then that those arcs are also congruent. Or, even better, in 1 circle, if we had 2 chords, and this is the one we use most, 2 chords in 1 circle are congruent, their corresponding arcs are also congruent. Okay, so look for that. Okay, so if I told you this arc was 30 degrees, this arc would also be 30 degrees. Corresponding chords congruent, corresponding arcs congruent. Okay, in Theorem 9.2, in a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. Then it bisects the chord and its arc. Okay? So an example of that would be if I got a circle, I got a chord running here, and then I have a diameter, so through the center point, okay, and it splits, the diameter splits the chord into 2 equal pieces, then those corresponding arcs obviously would be the same size as well. Okay, as well as forming a 90-degree angle. So if we got a diameter that splits a chord in half to 2 equal pieces, and it forms a right angle, it's a perpendicular, and it also splits the chord and arcs into equal pieces. Theorem 9.3. In a circle or in congruent circles, 2 chords are congruent if and only if they are equidistant from the center. Okay, so if I got a circle, and I have a diameter, sorry, scratch that. If I have a circle, and there's a center point right there, and we got two chords, like so, and they're the same exact distance. Remember, distance from a point to a line forms a right angle. So if these are the same, then the chords are also equal. So if I say this is chord AB and this is chord CD, that chord, so chord, which is a segment, would be equal to segment CD or chord CD. It has to be perpendicular for that to happen. It can't be any line drawn from the center to the chord. It has to be perpendicular to the chord. Okay, example 1. In the circle O, so O is the center, OD, the measure of O to D, is 15. And the measure of CD, from C to D, is 24. Now, because OE is perpendicular to arc CD, we go back up to our theorem 9.2. It bisects, so CE and ED are the same. They're the same size, which means that CE would be half of 24 as well as ED, which so that makes it 12. Now we have a right triangle. So now we have this. We have O here. We're trying to find X. We got E here. We got point D here. We know OD is 15. ED is 12. Guess what? Pythagorean theorem. X squared plus 12 squared is 15 squared. Solve your Pythagorean theorem. You should get 9 for X. Last example. We got a grate on a grill. Is in the shape of a circle with a diameter of 54 centimeters. The horizontal wires are supported by two wires that are 12 centimeters apart, which means that if this is the center of the grill, we got 6 here and 6 there. 6 to there, 6 to there. Okay. The grill is symmetrical and the wires are evenly spaced. What is the length of each support wire? Okay. So let's say we drew a right triangle and we found half the support wire, kind of like so. So we got 6 there. Okay, we're trying to find X. It says the diameter of the circle is 54 centimeters, so half of 54 is 27. So from the middle to the outside of the grate is 27. Use the Pythagorean theorem. X squared plus 6 squared is 27 squared. We'll estimate this. Okay, so we'll actually get, for X, we're going to get around, 26.3-ish approximately. And that's half the support wire. So if I double that, you should get actually 52.65 centimeters.